Annenberg Media.
Wow, I mean, these things are really beautiful. And this one, it's one of my all-time favorites. Well, you might not think of these as works of art. And I agree that in terms of looks, they don't hold a candle to the Mona Lisa. But they're masterpieces just the same. Now, this one here is the second law of motion. It was discovered by Isaac Newton more than 300 years ago, but it's still used constantly today, especially in the space program. Now, this is Einstein's famous discovery that a little bit of mass is the same as a whole lot of energy. That's E. It's the equation that ushered in the atomic age. And this is the timeless Pythagorean theorem. It lets you calculate the length of the sides of right triangles. It was discovered more than 2,000 years ago, yet it's still being used all the time. In the previous programs, we've learned some of the basic rules of algebra, rules for variables, exponents, and for combining terms. These are the same rules used by Einstein, Newton, and Pythagoras. Our ultimate goal is to be able to solve equations like these. But before we do, we need to learn how to work with some basic mathematical building blocks from which equations like these are built. Polynomials. A polynomial is a sum of algebraic terms with only whole number exponents on the variables. In this program, we'll see how to work with polynomials, how to add, subtract, multiply, and divide them. We'll learn how to simplify polynomials by factoring. We'll meet a special class of polynomials called the difference of squares and learn how to factor them. And we'll also learn to recognize and work with perfect square trinomials. Okay, so what's a polynomial again? It's a sum of terms with only whole number exponents on the variables. Remember that whole numbers are 0 in the positive integers, 1, 2, 3, and so on. In other words, these are polynomials. Polynomials with only a single term, like this one, are called monomials. Polynomials with two terms are called binomials. And polynomials with three terms are called trinomials. That's as far as mathematicians go with this business. All polynomials larger than three terms, like this one, are all lumped together and called just plain old polynomials. I've said that polynomials are mathematical building blocks. Well, just as you seldom notice the individual bricks of a finished building, you seldom notice the polynomial building blocks supporting a wide range of activities.
Yes, please. I'd like to...
When you go to the bank, polynomials are at work in the formulas used to compute the interest you get on your savings account.
Thank you very much.
Have a good day.
In architecture and construction, polynomials are essential in the equations used to determine the load-bearing capacities of steel beams and other building materials.
Okay, that's the first speed. You'll be there for just a little while.
In modern sports training, polynomials help trainers determine the optimal exercise and nutrition regimens for their athletes. And the aviation industry practically runs on polynomials. Everything from engine design to in-flight navigation depends on equations built from polynomials.
Now let's learn to work with polynomials. As we've learned before, when dealing with variables, we can only combine like terms, such as negative 6t to the fourth and negative 10t to the fourth. Here's an example. Let's add these two expressions together. Notice that the exponents descend from left to right. That's a mathematical convention to keep long expressions clear. Now, the best way to approach this is to combine the two polynomials one term at a time. Let's work with the first terms of each expression, 2y to the fourth plus 4y to the fourth. Since y to the fourth is common to both terms, we can factor it out using the distributive property to give us 2 plus 4 times y to the fourth. Then we can combine the remaining terms to get 6y to the fourth. Let's do the same thing with the next pair of terms, negative 3y squared and 7y squared. Again, we can factor or pull out the common term, in this case y squared, leaving us with the quantity negative 3 plus 7 times y squared. Adding negative 3 and 7 gives us 4y squared. Let's do the same for the last two terms, remembering that the coefficient of y in this case is 1. Pulling out the common y term leaves us with 1 plus 6 times y, which is 7y. So the result of adding these two trinomials is 6y to the fourth plus 4y squared plus 7y. Subtracting polynomials is accomplished in a similar way. Find like terms, use the distributive property, and simplify. Remember, before we subtract these two expressions, we need to arrange the terms so that the exponents descend from left to right. So in the second polynomial, we just need to reverse the places of the two middle terms so that we get negative 8y cubed plus 6y squared minus 2y minus 3. As before, we work one term at a time, starting with negative 4y cubed minus a negative 8y cubed. With subtraction, of course, you have to be careful to keep your signs straight. It helps to use parentheses. Here, for example, we see that the minus negative 8y cubed becomes 8y cubed. Then when you combine it with the negative 4y cubed, you're left with 4y cubed. Okay, what about the second term? That's negative 6y squared minus 6y squared. Combining the two gives us negative 12y squared. Next is 5y minus negative 2y. The minus negative 2y becomes 2y. And so the two terms combine to 7y. The last subtraction is negative 1 minus a negative 3. Again, the minus negative 3 becomes positive, and combining the two leaves us with 2. So our answer is 4y cubed minus 12y squared plus 7y plus 2. The distributive property is also used to multiply polynomials. For example, to find the product of these two expressions, treat the quantity 3x minus 4 as a single expression and distribute it across the trinomial. So that's the quantity 3x minus 4 times 2x squared plus 3x minus 4 times negative 3x plus 3x minus 4 times 5. Now, we can use the distributive property again 3 separate times. 3x minus 4 times 2x squared is equal to 3x times 2x squared plus negative 4 times 2x squared. 3x minus 4 times negative 3x equals 3x times negative 3x and negative 4 times negative 3x. And 3x minus 4 times 5 equals 3x times 5 and negative 4 times 5. Now we can multiply and combine like terms. Doing the multiplication gives us 6x cubed minus 8x squared minus 9x squared plus 12x plus 15x minus 20. Now we can collect our answers on a single line. Combine the like terms of negative 8x squared and negative 9x squared and 12x and 15x. And we're left with our answer, 6x cubed minus 17x squared plus 27x minus 20. Often in algebra, we need to multiply two binomials together. A convenient way to do this is called the FOIL method. It works like this. Let's multiply the two binomials 6m plus 1 and 4m minus 3. Now, FOIL is shorthand for the order in which we multiply the terms. So we have first, outside, inside, last. We multiply the first two terms at 6m and 4m, which gives us a 24m squared. Then we multiply the outside, 6m and negative 3, which is going to be a minus 18m. Then the inside, which is 1 and 4m, which is a plus 4m. Then the last, which is 1 and negative 3, which gives us negative 3. Now we can combine these like terms, and what do we have? We got 24m squared minus 14m minus 3 is our product. Let's try another binomial multiplication using the FOIL method. Let's multiply 3x minus 2/3 by 5x plus 1/3. The product of the first two terms is 15x squared. The product of the outside terms is 3x over 3. The product of the inside terms is negative 10x over 3, and the product of the last terms is negative 2/9. We can combine the like terms just as we would any other fractions. Since they already have common denominators, we can combine them directly. 3x over 3 minus 10x over 3 equals negative 7x over 3. So our answer is 15x squared minus 7x over 3 minus 2/9. Now we've seen that polynomials can be added, subtracted, and multiplied. We won't do an example of it, but polynomials can also be divided using rules that are again similar to those that you're familiar with. It's because we can work with polynomials in this way that we can solve equations made up of polynomials. The ability to work with polynomials is nowhere more important than in science. For instance, here's an application of polynomials that's really out of this world.
For a clever extraterrestrial, communicating across the vastness of space is easy. All you need is some string, an assortment of other household junk, and the magic of Hollywood.
It's working! It's working!
But what about real life? Are there really ETs communicating out there amid the stars? In the wooded countryside near Boston, one scientist is trying to find out.
I think it's extremely likely there's evolved life in the galaxy. And if we're typical, then there's evolved life that's both more advanced than we and less advanced. I think it's extremely likely that some of this advanced life is attempting to communicate. In fact, I believe that there probably already is communication among civilizations in the galaxy.
Horowitz is trying to eavesdrop on some of this communication. His primary tool is an 80-foot wide radio telescope, but he also relies heavily on mathematics. At every step in the search process, algebra and polynomials are essential, starting with the shape of the radio dish itself.
By the time a signal transmitted from perhaps 100 or 1,000 light years away has reached Earth, it will be very weak indeed. So it's important to gather as much of the signal as you can. And the way the radio frequency dishes, microwave type dishes work is that the surface is designed to have the proper shape to focus the radiation coming in back to a point. The shape is not arbitrary. There's a precise mathematical curve in this antenna, a curve that has the property that parallel rays are brought to a single point focus on the axis. At that point, we put our radio collecting horn and convert the signal to electrical currents from which they're amplified and brought into the control room.
It is in the control room that the real listening begins. The incoming radio signal is split into 8 million individual channels, each of which is analyzed by a powerful computer that Horowitz simply calls a box.
This box is really equivalent to 8 million radios sitting on your desk, each one tuned to an adjacent channel. However, we don't build 8 million radios. We do this by a mathematical process known as the Fourier transform. By computing Fourier transforms, we avoid the effort of building 8 million radios, which is a good way to go.
As the dish sweeps the heavens, all 8 million incoming channels are analyzed for signs of intelligence. One such sign could be a spike in the signal, a channel that is many times stronger than the natural background radio noise. Algebra is essential in finding such spikes and helping to determine if they are genuine messages or just stray signals from Earth.
You couldn't do this search if you didn't have mathematics, and in particular if you didn't have algebraic operations. The whole mathematics of communications theory, modulation and demodulation, is the mathematics of products and sums, of polynomials.
The polynomials and other algebraic operations, however, are seldom noticed once the equipment is designed and built.
After it's running, you take it for granted. When you start your car in the morning, you don't think about polynomials, although there's certainly mathematics underlying both the design, manufacture, and functioning of something like an automobile or a radio.
Even with computers and advanced mathematics, the search for messages from space is tedious work. It's been 3 years now since the search began, and nothing but the uniform hiss of the cosmos has been heard on the speakers in the control room. But Horowitz is patient, and he remains optimistic that his mathematical search for extraterrestrial life will one day produce proof that we are not alone.
I think that we're at the earliest stage at which we could possibly engage in this kind of communication, because our technology has only recently achieved the kind of capabilities that are needed to communicate across galactic distances. Therefore, if we do find a signal, and I think we will one day, I think it's when, not if, we're likely to be the less advanced of the pair, because we're just new at this game.
The search for life in outer space illustrates how polynomials are usually found in the real world. They're the basis for equations, which are the real workhorses of mathematics. Okay, now we've learned some basics about polynomials. Let's move on to another skill, factoring. As you may recall, factoring is essentially the reverse of multiplication. For instance, with multiplication, you begin with 37 times 3 and end up with 111. With factoring, you begin with 111 and end up with 37 times 3. 37 and 3 are called factors of 111. The process of factoring always requires you to look at a number or a term and figure out how to break it into two or more parts that, when multiplied together, give you the original expression. Here's an example. Let's factor 6x squared y cubed plus 9xy to the fourth plus 18y to the fifth. First, look at the coefficients of each term. What's the largest factor common to 6, 9, and 18? Well, each number is divisible by 3, and 3 is the largest number we can divide each number by. So 3 is the largest common factor of these three numbers. Now move to the first variable in each term. Notice that the first two terms contain an x variable, but not the third. This means that x is not common to all terms, and thus it can't be factored out of the entire expression. But there is a y variable in each term. And since the y variable with the smallest exponent is y cubed, that's the most you can pull from each term. In other words, we found that 3y cubed is the greatest common factor of the expression. So we can factor the 3y cubed from each term. In the first term, factoring 3y cubed leaves us with 2x squared. Factoring the second term leaves 3xy, and factoring the third leaves 6y squared. Now we can use the distributive property to bring the 3y cubed term outside of the expression, leaving us with 3y cubed times the quantity 2x squared plus 3xy plus 6y squared. One particularly common class of polynomials are trinomials where one term is squared, such as y squared minus 5y plus 6. Trinomials such as these can often be factored into the product of two binomials. Let's start with this trinomial. Since there's no common factor, we know that if the expression can be factored, it will factor into two binomials. So let's draw the framework of parentheses and work from there. Now, remember the FOIL method of multiplying binomials? We'll be using that method in reverse to find the factors of this trinomial. Let's start with the first term of the trinomial, y squared. Since by the FOIL method, we know we would multiply the first two terms of the binomials to get the first term of the trinomial, we know that our two factors must be y and y. Now let's look at the last term of the trinomial, 6. Again, by the FOIL method, we know that the product of the last two terms of the binomials is 6. So that gives us several choices. We could put a 1 here and a 6 here, or a 6 here and a 1 here, or a 2 here and a 3 here, or a 3 here and a 2 here. How can we tell which of these combinations is correct? Well, the middle term of the trinomial will tell us. The middle term is negative 5y. We know that this term is the result of multiplying the outside terms of the binomials, multiplying the inside terms, and adding them. So we need to find the combination of the factors of 6 that gives us negative 5, the coefficient of the middle term. There's no hard and fast rule for doing this. The best way is just to try a few combinations and see if they work. Our first clues are the signs in the trinomial. Since the last term is positive, we know that the two terms in the factors have to be either both positive or both negative. But we also know that the middle term of the trinomial has a negative sign. The only way for that to be is for both the terms in the factored binomial to be negative, because if they were both positive, we'd never be able to combine them to get a negative sign for the middle term. So now we've found the signs of our factors. The factors will be y minus something times y minus something else. So let's try a pair of factors for the last term. Let's try 1 and 6. We check this by using FOIL. First, that's y squared. Outside, that's negative 6y. Inside, that's negative y. And last, that's 6. Combining the two middle terms gives us negative 7y. But that's not what we're looking for. We're looking for the negative 5y in the original trinomial. So it's back to the drawing board. Since 1 and 6 didn't work, let's try 2 and 3. With FOIL again, we have first y squared, outside negative 3y, inside negative 2y, and last 6. Aha! Now when we combine the inside terms, we get y squared minus 5y plus 6. The answer checks. We factored the original trinomial into two binomials, y minus 2 times y minus 3. As you can see, factoring trinomials such as these involves some educated guesswork. By setting up the framework first and filling in the parts we know, we can save ourselves a lot of work. With a little practice, you'll be able to do the trial and error work for some problems in your head. Let's try factoring another trinomial. Again, the first step is to set up the framework. Since the first term is y squared, we know the first two terms of the factors are y and y. The last term, 72, factors a number of ways: 72 and 1, 36 and 2, 24 and 3, 18 and 4, 12 and 6, and 8 and 9. Now take a look at these possibilities, bearing in mind that the coefficient of the middle y term is 1. This means that somehow the two factors of 72 have to combine to leave a remainder of 1. Given that fact, the factors 8 and 9 seem like good bets since their difference is 1. Now, what about the signs? The last term is negative 72, so that means we need a positive factor and a negative factor. Now, at this point, we should just go ahead and try combinations of factors and see if they work when we multiply using FOIL. Let's try it this way: y plus 8 times y minus 9. Using FOIL, this gives us y squared minus 9y plus 8y minus 72. Combining the two middle terms leaves us with y squared minus y minus 72. Well, that's almost it, but not quite. What we want is a positive y for a middle term, not the negative y we just got. So let's switch the numbers. Now when we multiply, we get y squared minus 8y plus 9y minus 72. Combining the like terms this time leaves us with y squared plus y minus 72, which checks. So our answer is y plus 9 times y minus 8. Here are the key steps in factoring trinomials. Create a framework. Factor the first term. Factor the last term and examine the factors for pairs that look like they might combine to form the middle coefficient. Try some combinations of factors. And remember to check your combinations by multiplying using the FOIL method. There are a couple of special kinds of polynomials that you should learn to recognize because they crop up so frequently. The first is the difference of two squares. Here's an example: x squared minus y squared. Now, x squared minus y squared factors as x plus y times x minus y. Now, we can check this with FOIL. Remember, that's first, which gives us x squared, plus the outside, which is a negative xy, plus the inside, which is a positive xy, plus the last, which gives us a negative y squared. Now, negative xy and positive xy add up to 0, and so we're left with x squared minus y squared, which is just what we started with. Here's an example. Let's factor 4m squared minus 9. Notice that the two terms, 4m squared and 9, are perfect squares. That is, 4m squared is 2m times 2m, and 9 is 3 times 3. To factor the binomial, first set up your parentheses. Now factor the first term. As we've seen, the factors are 2m and 2m. The factors of the second term are 3 and 3, so we put them in the second positions. Finally, we know that the difference of two perfect squares will give us a positive and a negative sign on the factors, so we can just add the signs and we're done. It doesn't matter, by the way, whether you put the positive sign first or the negative sign first. The middle two coefficients cancel either way. Another group of polynomials that you should become familiar with are the perfect square trinomials. Unlike the last class of polynomials we examined, here we start with the trinomial and factor it into the square of a binomial. The same skills of recognizing perfect squares are used here. Let's factor 16p squared minus 40pq plus 25q squared. The two key terms to look at in looking for a perfect square trinomial are the first and the last terms. Here, the first term, 16p squared, factors into 4p times 4p, so it's a perfect square. The last term factors into 5q and 5q, so it too is a perfect square. Since this trinomial has a negative and a positive sign, we know that if it factors as a perfect square, it'll factor into the general form of x minus y times x minus y. Substituting 4p and 5q into this pattern, we can then multiply using the FOIL method to see if it works out. So that's 16p squared minus 20pq minus 20pq plus 25q squared. Combining like terms leaves us negative 40pq in the middle. Thus, the answer equals the trinomial that we started with, so we found the correct factors. Now that we've learned how to factor and how to spot a couple of important kinds of polynomials, such as perfect square trinomials, we're well equipped to handle a wide range of polynomial expressions. In this program, we've learned about mathematical building blocks called polynomials. We saw that polynomials can be added, subtracted, multiplied, and divided. We've seen that polynomials can often be simplified by factoring, and we've learned to recognize some specific kinds of polynomials that appear frequently. Of course, we also met some of the all-time great algebraic equations. In the next program, we'll use our skill with polynomials to begin solving equations like these. In the meantime, I'm going to use one of my favorite algebraic equations. Okay, so it isn't exactly on a par with E equals mc squared. It's pretty handy nonetheless. See, H stands for handicap. Bowling handicap, that is. With this little baby, I'm going to be a contender down at the alley. Talk about an essential equation.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.